Wait.
Okay, so, ooh,
Yep, I can hear you.
good.
Yeah,
Okay,
I
so,
can hear and see what I think I should hear and see. I'm going to mute
awesome.
now.
So Chris gave a pretty good introduction of the kind of the background of why we got into this. I'm going to be talking about these assemblies of gold nanomaterials, specifically what we call superclusters, which is just an assembly of nanoclusters into, this assembly of gold nanomaterials. So first off, just an introduction to what an assembly is. In this case, we're starting off with monomer units of gold nanomaterials, whether it just be a gold salt or a gold nanoparticle, on the left over here, a gold nanorod. In this case, they have individual rods. They're going to manipulate these in such a way that they assemble into specific shapes. Here, they introduced a sulfate ion, which changes the electrostatics of these gold nanorods so that they bind on their end-to-end rather than on the longer axis. On the right over here, this publication used gold salts and reduced into nanoparticles while manipulating the system with circularly polarized light in order to make these agglomerations of nanoparticles that were chiral overall and responded to polarized light. What we're talking about with assemblies is just, some sort of agglomeration of monomer units with an additional external stimulus to induce some sort of property change. Something's going to be different about the assembly than you had with the monomer unit. Hopefully you'll be able to control that and, pick what kind of properties you want to actually have here. The basis of this was on this Sorensen paper from 2009. In this case, they used gold nanoparticles protected by dodecane thiolate ligands. These were placed into a solvent mixture that's anti-solvent rich. So it was T-butyl-toluene as their solvent and 2-butanone as their anti-solvent, and they ran it at 96% anti-solvent, so 2-butanone. So very, very, very limited solubility, and they probed this with temperature changes in order to induce assemblies from these nanoparticles into superclusters. They would heat it up to 65 degrees Celsius and then do a quick temperature quench down to, in this case, 0, all the way up to 54 or so, and see what kind of superclusters would form over that time. They probed this using dynamic light scattering for the size of the superclusters formed. And what they saw was a kinetic nucleation and growth of the supercluster assemblies in solution. That meaning the deeper the quench, the more nucleation sites were available in solution for the monomer units. So the deeper the quench, the smaller the supercluster formed because you have more nucleation sites, and thus the monomer units spread into more different supercluster assemblies. We wanted to build off of this and see what kind of work could be done using superclusters that are, instead of almost 5 nanometers, about 0.7 nanometers core size or 1.2 solvodynamic radius, something around there, to see if we could make smaller superclusters and try and control their size better as well, because you've got more surface accessibility. The basis of the supercluster formation: at higher temperature, we have our monomer units separated in solution because of the higher solubility at higher temperatures. At lower temperatures, we reduce the solubility. These are going to assemble together into agglomerations, hopefully spherical. This could be done through intercalation of the ligands, kind of shown here, the alkane thiolate ligands interacting, or through gold-gold interactions from the surfaces, which you could get from the nanoclusters that you probably couldn't from the nanoparticles, because their surfaces are much more flat. Looking at the different kind of growth realms that you could have, On the left, we have the kinetic growth system that was accessed in the Sorensen paper, which is a short time scale, quick reaction growth of these assemblies. At lower temperatures, you have more nucleation sites, so you end up with smaller assemblies formed. At higher temperatures, less nucleation sites, so the monomer units will build into larger assemblies. Conversely, with larger timescale experimentation, you can access thermodynamic ranges. What we're looking at here is just stable size based on long-term solubility or stability in solution. At lower temperatures, you have lower solubility over time, so your supercluster assembly should grow larger. At higher temperature, you have higher solubility, so your supercluster should be smaller with more monomer units still in solution and not agglomerating. For our protocol here, building superclusters, we used gold 25 hexane thiolate, so following with that alkane thiol ligand that was used in the Sorensen paper. I tried this with phenylethane thiol, which is the kind of benchmark ligand that's used with gold 25, and couldn't create superclusters, so I went to this alkane thiol reproducing what they were working with. In the zero charge state, this was dissolved into my anti-solvent solvent mixture, which is 80% ethanol, 20% toluene. And then for testing the different growth systems that we can access, kinetic versus thermodynamic. For kinetic, it's the short time system, so we want to be able to change temperature very quickly. Here, once the gold 25 solution was in its cuvette, it would be heated within a water bath to 40 to 50 degrees Celsius. The DLS would be cooled down to the temperature that we want to quench at already. It would be pulled out of the water bath, wiped very quickly, placed in the DLS, and as quick as the DLS could take a measurement, we took a size measurement in solution. From the thermodynamic system, we just use the temperature control within the DLS. It sweeps very slowly from low to high temperature to stabilize, and then used a little bit longer wait times at the specific temperature that we were looking at for the size of the superclusters formed. To check that these were recyclable, they were heated up for deaggregation in between each quench measurement. Similar procedure to what was done within the Sorensen paper as well. And then once heated up all the way and they were deaggregated and tested in the DLS that we just had monomer units, they were quenched down again to form superclusters at a different temperature. So, like I said, we were using gold 25 hexane thiolate 18 in the zero charge state. On the left here, we have the MALDI mass spectrometry of this cluster showing purity of the material that we used for these measurements. Kind of hypothesis for how these would build together kind of was later thought of as very, very similar to this alkane thiol crystal structure by Moran and the electrocrystallization paper in 2017. Here, gold 25 and the zero charge state crystallized together with hexane or with pentane thiolate ligands. So similar alkane thiols, they also used butane thiolate ligands, and they grew crystal structures very, very similarly, where you have small interactions of gold to gold on the surface here. And you also see small intercalation of the ligands with these alkane thiols lining up together to interact within the crystal structure. This could be the same way that superclusters might be formed within solution, with the cores being able to interact because the gold 25 surface isn't completely covered. And there is solvent accessible gold on there in different crystal structures.
Hey Philip, can I ask a quick question?
Yeah.
So just on that last point you made, so I'm actually familiar with Flavio's paper, and so they looked at these alkane thiols, and my question is actually, you said you couldn't make a supercluster out of PET capped to gold 25, which is that just because the passivation was, there's too much steric hindrance from the ligand and therefore the cores couldn't interact with one another. But when you switch to these alkane thiols of like butane or ethane thiol, you can, because the cores
I
have a good
think
interaction affinity, some kind.
so it's just kind of empirically, I did not see superclusters form from this.
I
My
see.
thought was that you have to, with PET ligands protecting gold 25, you have to go to an extremely high solvent ratio
Okay.
or anti-solvent in order to get them to crash out at all. Instead of just 80-20, I'd have to get to about 98% maybe.
Oh wow.
And by that time, if I did any temperature quenching, it would powder out immediately. So maybe the interactions are a bit too strong with the pi-pi interactions, that they would just keep agglomerating.
Okay.
Was my thought.
Sure.
But I didn't investigate too much. Basically, it didn't work. So I moved on to a more similar system to the previous publication.
Okay. No.
Does
Thanks.
that answer?
Yeah, no, that makes sense.
Yeah. So let's move on to some experimental data that we found from this. So using that gold 25 hexane thiolate in the zero charge state, this is all done in 80% ethanol here. These were put into solution, heated to 40 degrees Celsius in the water bath, and then quenched within the DLS to these lower temperatures. And the measurements were taken as fast as possible with the DLS. 2-second wait period is after full calibration of the DLS. There's only so quick we can make the measurement here. So this would probably be about 1.5 minutes of total equilibration from time that it was pulled out of, or that it was placed into the DLS. So that's about as fast of the time scale as is possible here. And in this data set, we see a basic kinetic trend. The lower the temperature of the quench that was used, the smaller the superclusters formed. Like Chris said before, we were hoping to get a very discrete small number of superclusters building together, but most of the time these superclusters formed at quite large size. I mean, 120 nanometers. I did some calculations that I don't have in this presentation for sphere packing. And if these are packing mostly ideally based on the solvodynamic radius, that's near 1 million nanoclusters within the unit. So quite a lot of nanoclusters per supercluster. But we still see this kinetic trend. The lower the temperature quench, the smaller the supercluster formed because of that increase in nucleation sites. And in between each one of these measurements, the supercluster solution was heated back up, checked to make sure that it turned back into just 25 within the DLS, which DLS shows it at about 0.62 to 0.75 nanometers with the inherent error of the DLS there. Even though the crystal structure shows solvodynamic radius being about 1.2 to 1.5 nanometers. But we do show kinetic control here. On the opposite side, on the larger time scale with a similar procedure, we can show thermodynamic control over the supercluster growth as well. These are heated to the same temperature in between every measurement to make sure we're de-agglomerating these assemblies. But temperature control is done within the DLS, so equilibration time here with a 100-second wait period and the amount of time it takes to stabilize at the lower temperatures from 40 degrees, we're looking at maybe 5 minutes of equilibration at the temperature, so a much larger time scale here for these to grow into their thermodynamically stable supercluster size or assembly size. There's a very clear thermodynamic trend there, though. The lower the temperature of the quench, the larger the superclusters formed. This is a significantly different absorbance or based optical density concentration. I'll get into the complications of concentration in a little while, but we do see a smaller overall size of the superclusters in this case, for which I don't have a satisfactory explanation but this is much more on the realm of the size of supercluster that's much easier to work with for theranostics or any kind of other application of these. Combining kinetic and thermodynamic control is actually fairly simple once you get the concentration of nanocluster solution you're working with worked out. So I did that measurement as well, working with the water bath the same way as before, doing a very quick quench and just a 30-second wait time for the measurement here. 30 seconds was used instead of 2, because every now and then with different concentrations, it would actually take a little bit of time for superclusters to form. If you do a shorter wait time, it might not have already formed yet. But in this case, on the short time scale is the red data points here at 30 seconds, and 300 seconds is the blue. But within the exact same experimental parameters, the solution would be heated up, quenched, a quick measurement taken, and then allowed to sit within the DLS at that temperature for another calibration run and 300 extra seconds wait time. And these would equilibrate in solution and turn into the thermodynamically stable size at that temperature. So we can access both kinetic and thermodynamic control within the same exact solution just by changing the amount of time waited at those certain temperatures, which just kind of follows the normal behavior of a monomer and, you know, agglomeration two-phase system that we would think of. So moving beyond temperature control here, there are other factors that might change supercluster growth, nucleation and growth within solution. One obvious one is changing the solvent percentage worked at. This is some rough data that I'm planning on redoing soon. However, in this case, I changed the anti-solvent to solvent percentage. At lower anti-solvent percentages, so 75% ethanol, we see smaller supercluster sizes after waiting at 10 degrees Celsius, just to find what the thermodynamically stable size of the supercluster would be at that temperature. At higher ethanol percentage, higher anti-solvent percentage, we see larger superclusters formed because the solubility is lessened of the gold-25 monomer units. These were done at roughly the same optical density, just by eye. Need to redo this experiment with complete control over the concentration of these to make sure they're, you know, all else being equal, we'll see what solvent specifically does to this. And we see the error bars on the 80% ethanol here just being caused by DLS difficultness. Moving beyond solvent control to the most complicated portion of this work is the concentration control of the nanocluster solution. This is pretty difficult. These measurements were done using optical density at 400 nanometers, which is one of the transitions of this gold-25 hexane thiolate. Pretty good measurement for the concentration of these, but it's hard to calculate out exact concentrations. So ranging in optical densities, you'd think as you increase the concentration, you'd increase the size of the supercluster formed, being that they're all in the exact same anti-solvent percentage here. So the more monomer units you add in, the larger the superclusters that might be formed. And you might see that trend from about 2.25 to 1.1 or so. However, the error inherent in DLS kind of prevents us from making an absolute statement about how concentration can impact the supercluster formation, at least of the thermodynamically stable sizes. Just from trial and error, it seems like thermodynamically, it doesn't matter too much which concentration you use as long as you don't go too high. Once you get about, or above 0.8 or so, you start getting into not an assembly or agglomeration system. You kind of start getting into a crystallization realm where things don't want to deaggregate no matter how much you heat them back up again. It's just too concentrated and they won't break apart. But honestly, I didn't really see a clear trend for the concentration of these. With the kinetic control, there was definitely a sweet spot of a certain concentration. You couldn't go too high in order to get these to deagglomerate to actually do a kinetic quench, but you also couldn't go too low because it would take too long for them to agglomerate again, that you couldn't get that short timescale range, and you'd have a lot more polydispersity once you get into the very low concentration based on optical density. One more avenue of control that we looked at was changing the charge state of the nanocluster monomer. In this case, I tried gold 25, hexane thiolate 18 in the -1 charge state, which is supposed to be the most stable charge state of gold 25. For this, I had to use degassed solvents only because the ethanol toluene mixture would oxidize this very, very quickly back down to the 0 charge state. However, on the left here, I have before and after pictures of the gold -1, which is this slight orange color, to the 0 charge state, which is this hint of green kind of solution. We see I did keep it in the -1 in this case, but with the -1 charge state in the DLS, we only see core-sized solid dynamic radius. I never saw supercluster formation in these solutions, no matter how cold or how long it sat at 2 degrees, or how I might have changed this solvent ratio. I did change it up to 90-20 as well, or 90-10 as well. So it seems like there's no supercluster formation from this -1 charge state. There's a couple ideas as to why it might be like that. First of all, if this is based on a gold-gold interaction for these agglomerations, you could have the electrostatic repulsion of being a -1 core. More likely, because it's in the -1 charge state, this has a counter ion, which is tetraoctyl ammonium, which is a very, very bulky ligand covering an entire half of one of the surfaces, or an entire side, if you could think of it as a cube, kind of. And that could keep the ligands from interacting with each other and intercalating and keep these from forming superclusters. Like I said, I did increase the anti-solvent percentage, and it still didn't create any superclusters there until it just crashed out as a powder, like it did with PET. So, some conclusions based on the experimental work so far. We've achieved kinetic and thermodynamic growth system control based on the different timescales that were used for the temperature quenching here. This was done just with 25 in the 0 charge state superclusters. Shown a little bit of solvent control over the thermodynamically stable supercluster size in solution. The more anti-solvent you have, the larger the supercluster formed. And also temperature control based on the kinetic and thermodynamic systems. Gold 25 in the -1 didn't form any superclusters. I attempted gold 25 in the +1 charge state, but with this hexane thiolate ligand that's fairly stable for gold 25, these clusters were very unstable and fell apart almost instantly after electrolysis and oxidation to the +1 charge state. Moving forward from the experimental matters already found, it would be nice to do electron microscopy just for confirmation of these assembly formations. To start off, just going to do some drop casting. I'm a little worried about drop casting since this is such a solvent dependent formation of these assemblies. for drop casting, if we put a solution on there that has superclusters already formed and the ethanol evaporates before the toluene, that could significantly change the size of these or break them down into monomers and not see anything, even on TEM. In the future, we could try environmental electron microscopy or cryo-electron microscopy to try and do more active kind of screenshots of what's happening within the solution. Cryo-EM is what I'm leaning more into right now because I just recently tested my ethanol toluene mixture and found that it does glass very, very easily in liquid nitrogen. So I'm going to try that system as soon as we get some electron microscopy time or universities open back up to easier access. Beyond this, other things that I've looked at for future expansion are covalent attachment. I looked at a couple different ligand systems and tried a very easy kind of click reaction system. I can't remember what exactly it was to do this, but the fact of changing the ligands to something that wasn't just an alkane thiolate meant that my solvent system wasn't forming superclusters anymore. So this idea didn't work too well for me. I've looked at some other ideas, such as alkenes, that could bind together after, an external stimulus to permanently fuse these that might be similar enough to the alkane thiolates. But that's kind of a future expansion of the project to see if we can make permanent attachments of these nanoclusters into lump-size superclusters. So we could select the conditions to make a supercluster of a certain size and then freeze it in that size range exactly. So you could tailor whatever size fused supercluster that you might want based on just temperature quench differences, and then an external stimulus to permanently fuse these. Awesome. So, any questions over this?
Thanks, Philip. I was glad to hear that the solvent mixture glasses really easily. That's really convenient.
Yeah, that was actually a big surprise to me how easy it was to get it to work.
Yeah. Yeah, that was just kind of an initial comment, but comments or questions from the peanut gallery?
Hey, this is Gauri.
Yep.
I just have a question. Have you looked at the properties, what could be different from the monomeric systems?
So I've looked at the UV vis of it. So if I change the solvent system up to that 85% ethanol, 15% toluene, these at 25 degrees Celsius are in supercluster form shown in the DLS. And I've taken the UV vis of that, and it doesn't show anything significantly different. So if there are interactions within those superclusters, they're not significant enough to change the optical spectra.
Okay.
I haven't done any other physical properties measurements or optical beyond that.
I'm just curious, do they look like the same when you look at them? I mean, the morphology.
Yeah. Exact same temperature, exact same color. I don't really see any different clarity to the solution at all.
Okay.
Yeah.
Thank you.
I just have a follow-up question on that, Philip. So is there, I get optically from the extinction spectrum, it doesn't appear to be any differences in things from what you've done thus far, but are there any different properties that you would like to be able to access, or different morphology, like is there any key difference about having these like supercluster packing systems that like you could then use that for something you can't use the single monomer clusters for? Like, are there desired applications for using these superclusters?
I think it would be the ability to tailor a specific size. So, making a nanoparticle on its own, there's certain size ranges that are pretty easy to access through different synthetic techniques. But to change from 100 nanometers to 120 to 130 might be a little difficult, specifically. Whereas with this, if you could do small temperature changes to access, whatever size spherical supercluster you might want. If we could then covalently attach these, you'd have a ready-made system for making whatever size, gold nanomaterial you might want.
Okay. Yeah, makes sense. So something, and then another question I had was you were kind of getting at the end when you switched to a different like oxidation state of the cluster. Just
Yeah.
so I guess I guess my, we need to ask this a little more simple question, which is I don't quite understand the solvent component to this part. So what is it about having a very high anti-solvent ratio that would make gold 25 PET cluster just crash out? But then with the alkane thiol of some kind, some length, you don't need as high of a ratio. Like what's the reason for that? This 80 to 20 versus like 98 to 2.
Good question. The way that I've looked at it for most of this is that the hexane thiolate ligand is very unstable for gold 25.
Okay.
Yeah, I think because it's not actually that soluble in the system compared to PET, you have more of a wiggle room to find that exact solvent mixture and temperature where you could have a two-phase system. Whereas because phenylethane thiol gold 25 is so soluble and so stable over time in solution that I just think you don't have enough of a window to play with where you decrease the solubility enough to access that two-phase system.
Okay. Interesting.
Yeah.
So then, but I guess the connection that I'm trying to make between the beginning and second half of this talk, which is then in a cluster that has a certain oxidation state, you could maybe make a supercluster with an anion cluster if you change the ligand or the covalent attachment part. And then other clusters, no matter what the ligand might be, you can't form this supercluster morphology without if the oxidation state is plus or minus, given the circumstances. So is that like kind of a balance between the two of like assessing what's the role of the oxidation state, what's the role of the covalent attachment site?
Sorry, I didn't understand that fully.
So I guess my question is, I thought it was pretty clear from the beginning that the ligand was clearly important in determining whether you could form these superclusters or not. But then at the end, it seemed more like the oxidation state also plays a really important role. And so I was just like, what's the balance and ratio between the two? Like, which do you think is more important in forming a supercluster or not?
That's the thing. I haven't been able to probe too much of it. So I think changing the actual nanoparticle core to something larger might reduce that effect of that charge state might have, because your counterion will be significantly smaller compared to the whole surface of it.
Okay.
I think in that case, the ligand was actually more important than the charge state if you move to a larger nanocluster. In this really small system, the charge state is so important because you have core-to-core interactions right there.
Right.
And the counterion is so significantly large compared to the core of the nanocluster that it has a huge impact.
Right.
So I think there's ways that you could mitigate the impact of both of them.
Mm-hmm.
That you probably could change ligands from an alkane thiol to something else, maybe not, an aromatic thiol there, or an aromatic phenyl group on the end of your thiol, because those pi-to-pi interactions might be too strong.
Right.
But something else that you might be able to do more of a covalent attachment with a larger nanocluster.
Yeah, no, that's really cool. Yeah, that's definitely, as a spectroscopist, right, I can appreciate that of being able to access different size windows by changing the ratio of the, like you said, counter ion to the core, but that kind of thing. So that is pretty cool. So yeah.
Yeah. So I took, the other system that I work with a lot, gold 102, thiolate 44. That's protected by thiophenol. It's just an phenyl ring attached directly to the thiol. And I kind of put it in one of these solvent systems like this and played around a little bit in the DLS. and never got any supercluster formation from it. That again could just be from that pi interactions of the surface, because 102 gets a little bit finicky when you start changing the ligand. It's something that I could easily try with a different system, because I've worked with gold 133 a lot as well, and you can change ligands around a little bit more on that. I mean, even 144, we can make that with alkane thiols, and that would be a great system to try as well, since I've got some of that sitting on my desk. It's something that could be investigated pretty easily, actually.
All right, are there other questions or comments? Okay. Well, I think that sort of then concludes, this part of the meeting.